Sih from University of Michigan at Ann Arbor to our colloquium series. Vanessa graduated with a PhD in physics from University of California at Santa Barbara, working with David Avshalom in Spintronics. So in that sense, she has in common a lot of things with some of the people here in the department. And she did a postdoc with Professor Jelena Vukovic, right, that's in Stanford. Right. And then she joined the faculty of the physics department in Michigan in 2008. She's now associate professor there. She continues her work on spin-dependent phenomena in semiconductors, and she is the recipient of both an NSF Career Award and an Eric Forrest Investigator Award, if I'm not mistaken. So it is really a great pleasure to have her here, and because the trip from Detroit was so much more painful than we all anticipated. Here's a little token of our appreciation. We give this to our colloquium speaker as a memento of their visit here. And the floor is yours.
Okay, great. Well, thank you very much. Thank you for inviting me here. It's a real pleasure to be here and talk about some of our research, and it's been a real pleasure to meet members of the department here. So I'm going to talk about our ultrafast optical measurements of spin polarizations in semiconductors. So we're interested in studying how conduction electron spins and nuclear spins behave in semiconductors. And so I'll first start with a brief history of spin. So as you know, spin is an intrinsic property of particles, and it was postulated by Uhlenbeck and Gauss-Schmidt when they were graduate students in 1925 to explain puzzling features observed in hydrogen and X-ray spectra. So I like that this started off with spectroscopy, and this is a picture of Uhlenbeck and Gauss-Schmidt and another fellow, Kramers. And this picture I like also because it was actually taken in Ann Arbor, Michigan. So they were there for a little while, and this picture was taken in 1928. Another thing we know about spin is that it played an important role in the development of quantum mechanics. So the Stern-Garlock experiment showed that when you measure the spin of, in their case, a beam of silver atoms, instead of smearing out over different configurations, they only measured two values. And so it demonstrated they had quantization of angular momentum. And at the time, they thought that it was due to orbital momentum and not spin, because you can see this was in 1922, and the Uhlenbeck and Gauss-Schmidt work was done in 1925. So why study electron spins in semiconductors? So we're really interested in the interesting physics. So you could be interested in it because spin is a quantum mechanical phenomenon, so you can prepare and study coherent states. The physics of spin decoherence involves interesting things such as scattering and spin-dependent band structure. And then there are also interesting things that happen in a material. You also have other things around, like nuclear spins. You can have magnetic impurities and holes, and I'll talk a little bit about spin momentum coupling and spin transport. And then finally, semiconductors are a highly tunable environment. You can change many things about the material and see how these affect the spin properties, things like the density of the electrons, their mobility, how they're confined, whether they're confined in a two-dimensional sheet, like in a quantum well or in a quantum dot, and strain, crystalline orientation, electric field, and dopants. These all affect the spin somehow, and we're interested in learning how they actually do that. The other reason you might be interested in studying electron spins is whether they can help enable new technologies for information processing and communication. So if you wanted to use spins to encode information, you have a natural way to do so, because a spin of an electron can have two states, up and down, and so you can use that to represent the ones and zeros for your information. And so somebody coined this new word, Spintronics, which stands for spin transport electronics. And people are excited about this because this has the potential to integrate logic, which is currently done by controlling the flow of charge in transistors with magnetic storage, and possibly offer some new device functionality, possibly with lower power dissipation. So there is metal spintronics, so studying spin currents in metals. So it was discovered that if you just make a sandwich of two magnetic layers that are in between, in this middle of the sandwich is a normal metal. If you measure the resistance of this sandwich, it turns out that if the magnetizations are anti-aligned, you measure high resistance, and if they're aligned, you can measure a low resistance. And so this became technologically very useful because this would give you a way to measure the magnetization of a small magnetic bit or layer in a way that was more sensitive than just directly measuring the force of that due to that magnetization mechanically. And so very soon after this discovery, actually, commercial GMR field sensors were available, and now they're used in all hard drive read heads, and this is a huge industry. And of course, Furt and Gruenberg were also awarded the Nobel Prize in 2007 for this discovery. So there is ongoing work then in Spintronics. So some of it involves whether we can replace current memory with magnetoresistive random access memory. And the advantage for this is it would be non-volatile. You wouldn't need to constantly refresh it with currents, which requires power. And other memories have some downsides. So besides refresh, flash doesn't require constant refreshing, but it does require large voltages and has a limited lifetime of cycles. And so this review article calls MRAM possibly a universal memory. And there are some MRAM devices available, but I think because they're just more expensive or less compact, they're not ubiquitous. And but there are definitely things that could be done to help MRAM, and one of those phenomena, which is also interesting in its own right, is spin torque. That if you have a spin polarized current, you can use it to affect the magnetization of a nanomagnet. And you can even use that to drive magnetization reversal. You can also use that to produce microwave oscillations. So if you don't completely flip the magnetization, but you just tilt it a little bit, it will precess, and then you can produce microwave oscillations that you could then use for something interesting. So coming back to semiconductors, why are we interested in semiconductors? So if you wanted to do realize devices that can do all logic, communication, and storage, I guess I claim communication because semiconductors allow us to interface with light, and spin-based devices may have some advantages over charge-based devices. So in this paper, they did an analysis just assuming that if you wanted to control logic with charge, then you imagine that like the limit, the fastest you can do it, and the least energy required for you to do it, there is some limit, some fundamental limit, but spin would not have that same limit. This is another proposal paper written by Hanan Derry at the University of Rochester, where another problem with moving currents really quickly is that there is dissipation and crosstalk in metal interconnects. And on the other hand, you can imagine making a spin-based interconnect where instead of changing the current, you flow a constant current through this wire, and you just change the magnetizations so that you change the spin in this wire. If you do that, you can transmit information potentially, well, without the problems of crosstalk and dissipation. And so then you can move these spin wires closer together and get much higher transmission rates. So this is the prototypical spin-based device that one could imagine using for logic. So it's an analog of an electro-optic modulator. It consists of, in red, 2 ferromagnetic contacts, and one is used as the source of spin polarization, and then that spin polarization flows through the semiconductor, and then at the end, another magnetic contact measures the spin polarization at the other end. And it's like an electro-optic modulator because what you can do in a semiconductor is you can use a gate voltage to change the spin precession under this contact, and so you can change then at this output the direction that this spin, the final spin state, and then so you could go from having a maximum transmission and a minimum transmission. And in semiconductors, what enables you to do this is both the long spin coherence times, which corresponds to being able to drag these spins over a large length, and still have spin polarization at the other end of this gate, and the voltage tunable spin precession, which is enabled by a spin orbit magnetic field, which I'll explain a little bit in this talk. So I know in talks it's easy to sit back and relax and let me say things that don't make any sense, but please let me know if you have any questions. All right, so how do we introduce spin polarization into semiconductors? Because the materials that I'm studying are materials, are semiconductors like gallium arsenide. They're not magnetic, and so the spins of the electrons in the material don't have any preferred direction. So to give them some preferred direction, we could apply a large magnetic field, and what that will do is they'll give us a different energy for the two spin states. But that energy, related by this Zeeman energy, is pretty small. It's like on the order of 0.03 millielectron volts per Tesla. On the other hand, the KBT is on the order of 0.1 millielectron volts per Kelvin. And so to get a sizable spin polarization, you want to make this number larger than this number, and that tells you that you need to go to either very high magnetic fields or very low temperatures in order to do that. And that's not easy to do. Another way one could introduce spin polarization is similar to that dotted DOS device that I showed. You could inject spin polarized carriers from a magnetic metal. Another way you could introduce spin polarization is to make a magnetic semiconductor. And then finally, another way is to use circularly polarized light. And this is what we do in our experiments. And so let me explain how this works. So the reason this works is because in the materials we look at, like gallium arsenide, we have a valence band that is P-like and a conduction band that is S-like. And so if we then look at the optical transitions that are allowed between the valence band and the conduction band, it turns out that there is a different transition strength for these transitions. So this is a little bit hard to read if you've never looked at it before. But let's say, so the red arrows correspond to right circularly polarized light, and the numbers tell you the relative transition strengths of these transitions. So if you come in with right circularly polarized light, this transition will happen 3 times more frequently than this transition. So this allows us to produce electron spin polarization with 50% efficiency. Similarly, a standard way that one could use to measure the spin polarization is to detect the polarization of the light emitted through the combination. Yes?
When you say 50% efficiency, what does that mean? The
Yes.
ratio of one spin versus the other, or?
Yeah, exactly, yes. So that just means that, so I'm going to have 3 times as many here as over here. So I have 3 minus 1 divided by 3 plus 1, the total number of transitions. It's a good question, and I should put that on here. So the experiment we do is, as I mentioned in the title, an ultrafast optical experiment. And ultrafast just means we use a very short duration pulse of light. So our light comes from a laser that produces short pulses. And what that allows us to do is to both excite spin polarization at some specific time and also measure it for just a very short duration of time. So the analogy I like to use is if you have ever seen a picture of, I guess, either a horse running or a bullet going through an apple. I mean, that's a picture that's taken either, you could take a fast picture either by using a very fast shutter, or you could use a strobe light so that the light is only on for a very short amount of time and it just captures what happened that instant of time when the light was on. So by using a short laser pulse, we can get the same temporal resolution. And so we take pulses that come out of our laser and we split it into two paths. So one will be our pump. It's going to be circularly polarized and produce the electron spin polarization. And then what happens is that if we wait a bit, a few things can happen. So first, we can have some recombination. So by pumping, we left behind some vacant states or holes in the valence band. And then those states can get refilled from the conduction band. The trick here is that we started off with a few extra electrons in the conduction band. So even after recombination, we're still left with a few extra electrons in the conduction band. But even after these holes are filled, we are still left with some net spin polarization. So this allows us to measure spin polarization that exists even beyond the recombination time. The other thing that can happen is if we apply a magnetic field, the electron spins will precess in that magnetic field. And then what we do is we come in with a probe pulse that's separated by some time from this pump pulse, and we then measure the spin polarization along the direction of the laser beam with the probe pulse. And then our typical data looks something like this. So if the probe pulse comes right after the pump pulse, we measure maximum spin polarization. But if we wait until the spins have had a chance to precess 180 degrees, we measure a minimum, and so on. So we can scan the time delay between this pump pulse and this probe pulse to then map out this decaying cosine. And from this decaying cosine, we can get both this spin precession frequency, and we can also measure this decay time, which we're interested in, which is related to the spin lifetime of the electron spins in our material.
Is that actual data or is that a graphical representation?
Yeah, so this is a graphical, but I'll show you some actual data actually on the next slide. So this is a picture of what our experiment looks like. Well, we can't see the laser, but in order to control the timing between the two pulses, we just use a mirror that's on a scannable delay stage. So this is a Q-corner retroreflector. There's a stepper motor right here that's computer controlled. And then our sample sits in a cryostat that's between the poles of this electromagnet. And then this is what the actual data looks like. So this is for 3 different magnetic fields. So you can see as you change the magnetic field, you change the spin precession frequency. They precess faster and faster. And we can also fit this nicely to a decaying cosine to determine the spin lifetime. So this material, this data was taken on material indium gallium arsenide, which has a spin lifetime of around 5 nanoseconds at 30 Kelvin. That was not what I wanted to do. Okay. And so we can fit this data to determine the spin lifetime, tau, and then I guess the other parameter is we know what magnetic field we're applying, Planck's constant, and the Bohr magneton are the constants. So what we get is the Electron G Factor in our material. Okay, so a variation of this technique is to not put the pump and the probe pulse at the exact same location on the sample, but to scan them relative to each other. And you can see why we might want to do this, because this makes it kind of analogous to the device I was showing earlier, where we can have electric contacts and we can pump the spins at some location, and then because of an applied electric field, the electrons will then drift, and since the electrons all have spin attached to them, that means the entire spin packet will drift, and then you can probe them at some other location, because they'll have moved at some distance given their drift velocity in this time interval between the pump and the probe pulses. So if we do such an experiment and we plot the spin amplitude as a function of distance, we can measure data that looks like this. So this is for different applied voltages. So you can see as you increase the voltage, this is with a time delay of around 13 nanoseconds, the spin packet drifts faster, and also the amplitude decreases a bit because the spin lifetime decreases. The other thing that people noticed in doing this type of experiment is that you can also measure an internal field that the electrons experience. And even with no applied magnetic field, this internal field also increases as you increase the voltage. So this may seem a little mysterious at first, yes?
I was actually wondering about the earlier thing. Why does the spin amplitude decrease with a larger driving voltage? Do you just get more scattering?
Yeah, so you could get more scattering, you could also get more heating, and so those are reasons that would affect the spin lifetime.
Do you have any carrier extraction, or is that two insulating layers born in the semiconductor?
So there is carrier extraction, yes. But we typically put the contacts far enough apart.
So more than 100 microns?
Yeah, more than 100 microns apart. Great. Other questions? Okay. So where is this internal field coming from? These are just a couple of other plots from papers showing the effect of this internal magnetic field. So here is a plot. So pump probe distance is now this vertical axis, and time is now this horizontal axis. And so you pump the spins, no electric field, they just stay at the same place. You now apply an electric field, and they start to drift along this dotted line that's a guide to the eye. And then not only do they drift, and you can see the amplitude also decreases here as well, you also see that the signal becomes negative. So that's an indication of spin precession. It's not that the spin information is just lost, but it's actually processing to be negative. Similarly, this work by Scott Crooker at Los Alamos also showed that this internal field is related to strain. So if you do this experiment with an applied electric field on just a piece of gallium arsenide that's not strained, you just see that the spins diffuse, but they don't precess. On the other hand, if you then apply a mechanical vise and squeeze the sample, you see then that the spin polarization changes sign, and so that's an indication of spin precession. So there is some internal field acting on the spins and causing them to precess. So a way that Yui Kato developed to measure this internal field carefully is, well, if we go back to our equation that we used to fit the spin polarization, it was just an exponentially decaying cosine. But instead of varying delta t, now we're going to fix delta t in our experiment and instead change the applied, or in this case, external magnetic field. So there are then a few cases you could consider. So first is what happens if the applied electric field is 0. So in that case, you would expect that you would just measure a cosine, because you're just changing the magnetic field. It turns out we measure these things that look like Lorentzian peaks. And the reason we do that is because the spin lifetime is so long that we get contributions from previous laser pulses. And so the way to think of that is shown in this picture here. So our laser doesn't produce just one pulse. It produces pulses every 13.1 nanoseconds. And if we're at special magnetic fields where our laser pulse comes in after a multiple of 2 pi rotations, then we end up with a constructive interference. And similarly, we can have destructive interference. And so that accounts for these sharp peaks. And this is called resonant spin amplification. And another case we could have is, okay, let's apply an electric field, and let's apply the electric field perpendicular to the applied magnetic field. So when we do that, when Yui did that, he found that he goes back to measuring a cosine, and this is because once you have an electric field, yes, you have multiple pulses, but they'll have drifted different amounts, different distances in different amounts of time, because one of them will have drifted for 13 nanoseconds, but the previous one will have had a chance to drift for 26, so it'll have moved twice as far. And so you won't measure this sum anymore. You're back to measuring just the contributions from one pulse. And you measure a cosine, but this cosine is shifted by a little bit. And so that little bit is this internal magnetic field. So you need to apply some external field to cancel the internal field to get back to 0. Another case you can have is you can apply the electric field parallel with the applied magnetic field. When you do that, you get a cosine that's now symmetric about 0 applied magnetic field, except that the center peak is smaller than the other peaks. And the way to understand this is the internal field is perpendicular to the external field now. So you can never cancel it out with external fields. And so the total magnetic field will be given by the square root of the external field squared plus the internal field squared. So this was a way of not just measuring the magnitude of this internal field, but also establishing what its direction is and how it's related to the electric field. So in the measurements that Yui did, he found that this internal field is always perpendicular to the applied electric field. So where could this come from? So in our materials, there is also a spin-orbit interaction. So not only is there Zeeman splitting, but there's also the spin-orbit interaction. And what you can see when you compare these two terms, they look very similar. They're both something dotted with S. And so that tells you that this is this acts like a magnetic field, and it's a momentum-dependent magnetic field. And we see that in our experiments as well. That increases linearly with the magnetic field. And it also is nice because, as I'll show you, it offers a way to electrically control spin polarization. So then to understand what it actually looks like in gallium arsenide, we have to know something about the symmetry of the crystal and this spin-orbit interaction, what it does. I guess what I'll just say is that there are two linear terms for the spin-orbit interaction, and they have these dependencies on momentum. The interesting thing is that one of them is, I like to call it isotropic. No matter which direction you head in the crystal, the spin-orbit field is always pointing to your right. On the other hand, there's this other term that's allowed where the direction of the spin-orbit field depends on the direction of the momentum relative to the crystal axis. So this is an effect that depends on both the magnitude and direction of electron momentum. And then because we have this spin splitting, one could imagine that applying an electric field might be enough to produce an electrically generated spin polarization. And indeed, this was work that was done while I was a graduate student and showed that when you apply an electric field, there are two phenomena that can occur. So one is a spin current that produces, so that's shown by these green arrows. So there's some spin-dependent scattering that leads up to a buildup of spin polarization on the edges of the channel. And then there's also an electrically generated spin polarization where the spins are pointing in the plane of the sample, and it's uniform. It's like everywhere in the channel. And the first phenomenon, the spin Hall effect, its mechanisms, I think, are relatively well understood. On the other hand, this current-induced spin polarization, the blue arrows, it's also present, but the mechanism and how it depends on sample parameters is still an open question. And in particular, what was very perplexing about it is that measurements on different materials, on different samples, did not show a clear trend. And so you could ask, well, is it because it doesn't depend on anything? Or, I mean, it should depend on something. So we wanted to figure out whether there was anything in particular it might depend on. And the problem with comparing different samples is, I mean, how many people are experimentalists? Experimental condensed matter. Yeah, so you know that, if you make different samples, different batches of samples, things may vary day to day, that you might not know what exactly is changing, and so it can be very frustrating. And so we were also having the same issues, even comparing devices on our same wafer that was obviously grown on the same day. My graduate student designed a sample that we hoped would give us a more controlled environment. So basically, this is a device that has 4 contacts. And what it allows us to do is to change the direction of the electric field, so that will change the direction of the net drift momentum in the sample, but allow us to optically probe the exact same spot for all of the measurements. So this was another question mark we had. Maybe different samples have different amount of dirtiness, and so optically we're just getting different results. Well, in order to really roll that out, we want to be able to measure the exact same place all the time. So we can do just some relaxation simulations to convince ourselves and figure out what voltage combinations we need for different electric field directions. Then the fun part, we then have a couple of parameters we can now change. So one is the direction of the net drift momentum relative to the crystal axis. And then the other is, this graduate student was very enterprising, so he also figured out how to rotate our cryostat so we could change the direction of the magnetic field, the applied magnetic field relative to our sample as well. Question? Okay. And so the reason we want to do that is we wanted to figure out whether this electrically generated spin polarization was related to the spin-orbit field. In our sample, we have both of the two spin-orbit fields I showed you earlier, the isotropic one and the anisotropic one, in a 1:2 ratio. And when you add those together, you just add those vectors together, you find that you get this plot. And what that tells you is that for different directions of the momentum, you have different directions of the spin-orbit field and different magnitudes of the spin-orbit field. So, okay, so now that we have the sample, let's go ahead and measure the spin-orbit field. So this is examples of the spatially resolved pump probe measurements and the measurements of the internal field on that sample. We can both measure the internal field that's parallel with the external field and perpendicular, and so we also know the direction of the spin-orbit field in addition to the magnitude. And then we repeat this for different directions of the electric field. So when we do all of that, we did this with like the 15 degree intervals. So this is the magnitude of the spin-orbit field in 1 units. This is the direction of the spin-orbit field relative to the applied magnetic field. The lines are fits, assuming only contributions from the two linear terms for the spin-orbit field. And then, as you can see, we also made two samples from the same wafer, and these two samples gave us different results. And at first you might say, well, why is that? This is something that perplexed us as well. So our samplers are grown to have some strain intentionally in order to make the spin-orbit fields larger. But the downside of that strain is that there can also be inhomogeneous strain relaxation. So the strain is not the same across the wafer. And so because of that, these terms, the spin-orbit fields are related to strain as well. And so they have different values. But it kind of gave us a nice comparison because you can see that these have pretty different behavior. So in one of them, the ratio of the two spin-orbit fields is around 0.9, and the other was 2. Okay, then the other thing we did was to measure the corresponding electrical spin generation efficiency. So this experiment is a bit simpler than the pump probe experiment. We block the optical pump, so we're not pumping spin polarized electrons, and we just measure the Faraday rotation that's related to the applied electric field. So when we do that, we measure these odd Lorentzian line shapes. And the way to understand them is, so now we're measuring something that's steady state. We have no timing resolution anymore. And when the applied magnetic field is 0, the spin polarization is in the plane of the sample. So it's perpendicular to our laser, and so we measure 0. What happens when we apply an external magnetic field is it causes the spins to precess out of plane, and then we measure some signal. And then, but not only does it precess out of plane, so it precesses out of plane, but it also relaxes, and so that accounts for the finite width of this odd Lorentzian. So if you take like an exponentially decaying sine function and you take an integral over all time so that you get the steady state value, you get an odd Lorentzian, which is what we measure. And so we're interested in comparing how this amplitude depends with electric field. And so then we have some value for this electrically generated spin polarization amplitude, and we have our spin-orbit field magnitude. And we were expecting that these things would increase monotonically. so that there might be a linear relationship between the two, because this is related to the energy splitting, and we thought this might be related to that as well, but in fact it seems to be inversely related, which is kind of puzzling. So we don't have an explanation for that. We've talked to a few theorists, but not gotten a clear answer. We also, what kind of motivated us to work on these 4 terminal devices is that we also did measure devices with fixed directions, and we also saw this behavior, but at the time we thought, oh, it's because we're not controlling something in our experiment, or we're not getting very good reproducibility, but actually it was probably the same thing. So the electrical spin generation efficiency just seems to be smaller for crystal directions corresponding to a larger spin-over field. And on the other hand, these two devices, the data doesn't lie on the same line. So perhaps the ratio of alpha and beta is also important. So, okay. All right, any questions? So maybe go through this a little bit more quickly. Now that we have polarization in the electron spin system, that polarization can become transferred to the nuclear spin system through some spin flip interaction. And if you have a nuclear spin polarization, that produces an effective magnetic field that then will affect the electron spin precession frequency, which we can then measure. So this is the contact hyperfine interaction, and then this is the Overhauser effect. And so we're interested in seeing whether this electrically generated electron spin polarization would be transferred to the nuclear spin polarization. And the reason technologically we might be interested in doing that is because the nuclear spin polarization has a much longer lifetime. It's typically on the order of minutes. So for what we expected to measure, if we change the voltage, we expected to see a quick switch in the internal effective field because we have the internal field due to the spin-orbit interaction, and then a buildup of polarization, and then a slower increase in the total magnetic field due to the nuclear field. And when we started to measure it, we were reassured that this was indeed what we saw. And so the way we measure this effective magnetic field was by taking some measurements of an optically generated spin packet and then measuring how it evolves. So this gives us the frequency that is the spin precession frequency due to the total magnetic field, which is the applied field, the spin orbit field, and the nuclear field. And we kind of optimized this so we could do the scan with the fewest number of data points, but still give us a low measurement error. So this delay scan can be completed in 40 seconds with a measurement error of around 50 microtesla. So this is just a plot of the same data, but now as a color plot as a function of lab time for voltage switches at 0 and 10 minutes. And if we then fit this data to get the total magnetic field, indeed, so this is shown overlaid for 2 voltage switches, 0 to -2, 0 to +2 volts. We can then fit the nuclear field from this data, and so this was a current-induced nuclear polarization that was different than what had been previously reported, and the way to show that it's related to the electrically generated spin polarization is that it depends on the direction of the current. So if this was just a heating effect, then it wouldn't depend on the direction of the current, and this also shows that we can use this effect to align nuclear spins both with and against the external magnetic field. Okay, so another thing that we came across kind of unexpectedly, so there had been work showing that one could electrically tune the Electron G Factor in a device with a top gate voltage. So this basically was in a special quantum well, and then when you apply electric field, you tilt this quantum well, and when you tilt the quantum well, you displace the electron wave function from being in the middle of the well to being a little bit closer to one of the sides. And because the Electron G Factor depends on material, it's different for gallium arsenide and aluminum gallium arsenide, which is what was the barrier. This would change the spin precession frequency quite dramatically. And then more recently, so this is actually from John Salas's group, now he is at IBM Zurich, his group showed that when they did these measurements in quantum wells with an in-plane current, they also saw the G factor change a little bit, and they weren't sure why. So this motivated us to just look back in our own data, because we were always fitting it to get this Spinorbit field. We were also spitting out the G factor, but we weren't looking carefully at that data. But when we looked carefully at the data, we saw that we also saw that the G factor changed with electric field. And we also don't know why, but because we see it in a bulk sample and not just as they did in a quantum well, we know it can't be the top gate. It can't be an effect related to displacing the electron wave function in the barrier. So finally, in the last few minutes, I'll talk about spin noise spectroscopy. And so I'll start by saying that our optical pump probe techniques that we use are great and a lot of fun, but they require optical pumping. And whether we like it or not, the pump pulse is perturbing the system. So both intentionally, it's producing this spin polarization, but also unintentionally, it's also heating the system, it's generating photoexcited electron holes. And so you could ask, is there a way to measure the same dynamics that we measure, but without optical pumping? And so this experiment, I guess the first measurements in semiconductors was demonstrated by the Ostrike group, but before that there was work by Scott Kirker at Los Alamos. So this experiment is fairly simple, so there's no optical pumping here. A laser diode is just sent through the sample, and the Faraday rotation, which is related to the spin polarization along the direction of the laser, is then just recorded, and or sent to a spectrum analyzer. And this is because even though there's no optical pumping, there are still fluctuations, stochastic fluctuations of spin polarization, and then that spin polarization will still evolve. And so if you apply a magnetic field, you will measure a signal at the spin precession frequency at the corresponding magnetic field. So here's the data that would convince you that you change the magnetic field and you measure a peak at the spin precession frequency, and indeed this frequency changes with magnetic field in a way that's consistent with the Electron G Factor of this material. And then you can also fit the width of this curve to determine the spin lifetime. The downside of this technique is that you can see that the frequencies here are fairly low. And there's another version of this technique where instead of sending the signal to a spectrum analyzer, you then digitize it. And then you just take your stream of digitized data and you Fourier transform it. So it does the same thing that the spectrum analyzer does, but just digitization and then subsequent computer processing. But then the frequencies that you're limited to are determined by your electronics, or in the case of the digitization, how quickly you can digitize the signal. So that affects your resolution and affects the maximum frequencies that you can measure. So then there was a theoretical proposal in Germany that I haven't cited here, but then also followed up by an experimental demonstration of this technique, that you can go back, you can get the timing resolution of ultrafast spectroscopy by using an ultrafast technique. So what I mean by that is you can use short duration optical pulses, and the timing now will be determined, the temporal resolution will be determined by the duration of the optical pulse, and the dynamics you measure will be determined by this delay time, delta t, between two pulses. And if you send these two pulses through the sample and measure a term related to the sum of the signals squared, you will measure a cross term that's related to the correlation function. And so this shows you what their setup looks like, which is similar to the setup on the previous slide, but now with two short pulses. And in order to eliminate the background noise, the non-spin dependent signal, they also used a modulation technique, a polarization modulation technique. So they alternate between measuring signal, no signal, signal, no signal. And then the output of this that you expect to get as a function of this temporal delay is this correlation function. And so again, this gives you the signal as a function of delta t, and this is related to the spin lifetime and the spin precession frequency. So we set this up in our lab. A couple of modifications we made is instead of using the digitizer, the filter and digitizer, we instead use analog electronics to do this calculation, the sum and the square. And so the first thing we wanted to demonstrate was that we could again get the spin correlation function. So this is the delay time. So this is again giving us information on the time scale of picoseconds, but now without optical pumping. So we're closer to what happens in our sample without perturbing it. And then the other thing we wanted to do was to test our understanding of how to model spin noise. And so we did measurements now at a fixed temporal delay, but as a function of the magnetic field. And so the interesting thing is that naively we were expecting that we would just measure what we saw in this blue curve, which is the cosine. But instead, when we went to lower temperatures, we saw the emergence of these sharp peaks. And these sharp peaks are related to the fact that we're measuring not just correlations between pulses that are separated by delta t, but also correlations between pulses that are separated by delta t plus t rep, the repetition rate of our laser, and subsequent correlations. So those interfere to give us these sharp peaks, similar to the interference that I mentioned, the resonant spin amplification. But this is actually a nice feature in that if we just did our measurements this way, we're limited to a particular delay time range, and also the repetition rate of our laser would then produce something funny looking later. We wouldn't really be able to scan beyond that repetition time. So that would make it hard for us to measure spin lifetimes that are long relative to those times. On the other hand, this technique allows us to measure spin lifetimes on the order of 30 nanoseconds just fine. So we compared that what we measure through this spin noise spectroscopy is comparable to what we measure with on probe, and the resonant spin noise technique allows us to more accurately measure lifetimes that are longer than the delay range and the laser repetition period. Okay, so with that, I'll conclude. I've given you, I think, a whirlwind, fast view of a few recent results in our group. The first of which was that unexpectedly, we found that the magnitude of electrically generated spin polarization was larger for momentum directions corresponding to smaller spinorbit fields. This electrically generated spin polarization could be used to produce nuclear spin polarization. We also saw that the Electron G Factor had changed due to an in-plane current, and that this effect is important to take into account. Also finally, spin noise spectroscopy allows us to measure spin dynamics without optical pumping, and we've demonstrated a resonant spin noise technique and developed a model that we can use to fit this data. Thanks for your attention.
Do we have any questions from the audience?
Yes.
For these interference peaks that you get from the successive pulses, is it possible to use some kind of a pulse picker or a lower rep rate laser, or is there something specific about this laser that you have to have with that one?
Yes, so right. So we could get rid of those additional signal contributions if we used a lower rep rate laser, or if we used a pulse picker to reduce the repetition rate. It turned out to be, so we thought our electronics was fast enough that we wouldn't get signals from successive repetition periods. It turned out to be kind of a bonus feature, and that it did allow us to get something that allowed us to measure longer spin times.
Questions?
Yes.
I followed some of the Spintronics motivation, but I missed why you care about the nuclear spin hyperpolarization. Like, why do you want to be polarizing that? Just to affect the lifetime of the spin, or because it's neat physics, or something else?
Right. Well, actually, all of the above. So some groups are interested in doing in using electron spins, single electron spins, say in quantum dots, to do quantum information processing. And it turns out that the fluctuating nuclear spins gives you like kind of a limit it becomes like the dominant decoherence mechanism once you've ironed out other things. And so, but you can get a longer electron spin lifetime if you hyperpolarize the nuclear spins so that they're no longer fluctuating. So it's both to understand kind of how the electron spins and nuclear spins talk to each other. It was also, we read some nuclear spin literature, and people had talked about current-induced effects, but related to hot electrons like heating, but not related to this mechanism, and so we wanted to see what was the contribution of both. Yes?
So in your measurements, do you always apply electric field so the electrons moving?
Not
Not
always,
always.
but recently we've been interested in what happens when we apply electric fields so that the electrons are always moving.
Okay. So if you apply electric field as electrons moving, what is typically drift velocity of the electron?
So the mobility is on the order of like bulk gallium arsenide, so 1,000 centimeters squared per volt second. So you can see from the plots they drift roughly 150 microns in,
Yeah, I see
in 13 nanoseconds, right?
Oh, okay. So
That's
that's
the velocity.
Yeah, Sankita.
How's the drift velocity related to the G factor that you're calculating? What's the relation?
Right, so it's not, they're not really related, and except through this recent work where we've shown that the G factor and the drift velocity, we show that, well, this is more as a function of current. So at a particular current, we have a particular drift velocity, and we have a particular G factor. But I don't know if just changing the drift velocity would change the G factor. Yeah, so we don't really understand why this G factor changes with drift velocity. So the simple answer, so it's not lattice heating. I mean, because we can also measure the G factor as a function of sample temperature, and that changes. I think this G factor change would correspond to like a 9 Kelvin temperature change in our sample, and we're pretty sure that with these voltages we're not heating up our sample by 9 Kelvin. But on the other hand, the electron temperature, of course, is a lot higher, and but it's harder to control.
Any other questions? I have a few.
Okay.
A couple. So also related to this, but related to your conclusion, your first conclusion, right? So where does the diagonal pattern scattering come into this whole picture? Because you're talking, I'm assuming, about something that's n-type doped, right?
Right, it is n-type tope.
So you have electrons, you have conduction electrons, right? It's a current flowing there, so.
Right, and the diagonal is the dominant spin relaxation mechanism.
So that's dependent on the momentum, right?
So that depends on the momentum. Right, yeah, so if you have larger momentum, you also have larger diagonal spin relaxation. So I didn't go into the details of this electrically generated spin polarization, but when we plot this eta, this electrical spin generation efficiency, it's not just the amplitude of this curve. It's in a sense, it's the amplitude divided by the spin lifetime. So we came up with, I guess, a phenomenological model where we have spin precession, spin decay due to diagonal or other mechanisms, and also electrical spin and spin generation, some spin generation rate. And so if we put those together and then solve that equation, we can actually get and apply magnetic field. We can actually, so these solid lines are actually curves using that model. So this is for different directions of the external field relative to the internal magnetic field. And so since it fits pretty well, we think it's a reasonable model for what's going on. But that allows us to then, we're not, this steady state amplitude, you also have to take into account the spin lifetime in order to get the electrical spin generation rate. We're not just interested in the steady state amplitude because it's related to both the generation rate and the decay. So that will add up to give us some steady state value. So we measure the steady state value and then we back out from the spin lifetime what the spin generation rate is.
And the other question was really quick. So the indium is there to have the strain, right?
It is.
From the substrate. So when Scott and I were doing the first measurements in Los Alamos, we had a mechanical vise that actually strained the very pure gallium arsenide film. So is that better or worse than this method in terms of getting the uniform strain? I'm sorry, I'm kind of ignorant about this biaxial strain that you get through the growth, and so I don't know, is that a better or which one's better, you think?
Right, so
you get rid of this strain homogeneity problem, right?
Yes, so I think that would actually be better. So when I was in Santa Barbara, I also worked with a student who developed a 3-point and then a 4-point bending vise. And you can also then do some numerical modeling to figure out what the strain profile should be. And it wouldn't have this problem of inhomogeneous strain relaxation. So the problem is our samplers are grown above the critical thickness, which if you're in material science, you know that means that it's no longer, there's strain relaxation. It's the film is too strained to stay coherent with the substrate.
Questions? There's no more questions. Let's thank Vanessa again.